Good morning and welcome to this lecture in our mechanical operations course. So, the topic that we are going to take up today is mixing. Mixing is a very important mechanical operation in many industries because in many processes you have several ingredients that need to be brought together in intimate contact in order to make a certain product. And so, mixing and the effectiveness or completeness of mixing are critical parameters in running a successful operation. Now, when we talk about mixing, clearly the mixing of two liquids is very different from mixing of a paste or two powders, solid particulate materials. As you can imagine, and I am sure you have had again practical experience with this in your homes, when you are trying to blend a couple of liquids together, especially if they are miscible liquids, you can expect to get virtually complete mixing, where the concentration of each of the liquid is very uniform in the final blended mixture. Whereas if you are trying to blend together, for example, let us say you have sand and salt and you are trying to mix them together, even under perfect mixing conditions, you are never going to get a mixture that is perfectly uniform in concentration. And so the challenges of mixing of particulate solids is very different from the challenges of mixing liquids or even mixing a paste. So, some of the fundamental differences between the two, first the mechanism. How do you mix two liquids together? You use some kind of a mixing device, could be a stirrer or an impeller. So, the way it works, it is actually based on a transport mechanism. You are trying to bring the unmixed portion of the liquid close to the impeller so that it gets mixed. So, you try to set up a flow pattern so that the unmixed material comes into the proximity of the impeller, gets mixed and then gets thrown away from the location of the impeller, and you keep doing this in a continuous loop, right. Whereas in the case of mixing of particulate solids, you really cannot rely upon that. You cannot rely upon a transport mechanism to bring the materials close together, and in fact you may have to physically lift the materials and bring them next to each other in order for mixing to happen. So, it is a much more energy intensive mechanism. So, the power consumption involved in mixing of solids is much higher compared to the mixing of liquids. The second point, as I mentioned earlier, complete mixing can never really happen when you are talking about solid particulates. The definition of complete mixing is if you have a mixture with more than one constituent, you should be able to take a small sample anywhere in that mixture and look at the concentration distribution in that small sample, and it should be the same wherever you sample and however small the sample size is. So, if you have a vat containing several liters of a solution, when you take a milliliter from it and you look at how the concentrations of the constituents are in that small sample, it should be the same wherever you take this milliliter sample from. That is a definition of complete mixing in a liquid. However, in the case of mixing of particulates, what you would find is that your definition of uniformity depends on that sample size. In fact, there is usually a minimum sample size that you cannot go below in order to test for uniformity. So, you can imagine that if you have tons of a blend of various solids and you take a milligram from that, the chances that you will find a uniform concentration distribution in that small sample is actually pretty low. Whereas, if you take a 1 kilogram sample, chances are if you take multiple samples of 1 kilogram each, the likelihood that the concentrations are similarly distributed in these samples is much greater. So, the definition or the measurement of uniformity very much depends upon the sample size. So, that is the other factor that you have to keep in mind. Another thing to remember is mixing of particulate solids in some ways is an art, not a science. There are two reasons for this. One is that every solid particulate mixture is different in its nature. So, you cannot have a single process that works for all particulate mixtures. Whereas for liquids, you can pretty much say that if a process works well for one set of liquid constituents, it will work for any other. So, the fact that you cannot treat all solid mixtures the same means that it is not a science, right. I mean, science depends upon repeatability and reproducibility, and the mixing of particulate solids is not a repeatable and reproducible phenomenon, and also it is very time dependent. So, you might have again observed in your kitchen, you may be trying to mix some dough or something, the composition of that powder may be dry and segregated solid particulates at the beginning of the blending process, but then you add some liquid to it and it becomes pasty and it becomes more and more viscous, more and more stiff as you keep mixing, but eventually you may again get back to a stage where the material kind of breaks apart and it's in the form of loose solid particulates. So, the nature of the blend itself changes as a function of time. So, these are all challenges in mixing of particulate materials, and therefore, the design of industrial equipment for mixing of particulates tends to be quite complex, and it is a high energy consumer. Now, how do you define mixing effectiveness? In the case of liquids mixing, that is easy to do. You can take spot samples, analyze the concentration using whatever technique is suitable, and you can verify how uniform the concentration is. You can take several spot samples, and if the concentration distribution is about the same in each one, you would say it's well mixed. However, the measurement of the mixing effectiveness tends to be again a lot more complex in the case of mixing of pastes or particulate solids because of some of the issues I mentioned earlier. Also, the requirements for mixing of particulates is very different from the mixing of liquids, because there are really three objectives you can think of. One is the completeness of mixing, the second is the time required for mixing, and the third is power consumed during mixing. In the case of mixing of liquids, the three kind of go together. The longer you do it, the more power you put in, the better the mixing, but a lot of the mixing happens in the very first stages of mixing. So, you do not have to worry too much about optimization. In the case of mixing of solids, these three are sometimes conflicting and sometimes highly orthogonal. For example, if you want good completeness of mixing, you may have to do it for long periods of time, but then if you do it too long, you can actually have non-monotonic behavior where the material again starts segregating or agglomerating, and therefore you lose your mixing effectiveness. And certainly power input has a nonlinear dependence also because of the change in the nature of the mix as time proceeds. Typically in the case of mixing of a paste or a solid powder, the power requirement for each increment in mixing increases with time. So, that again it is a law of diminishing returns kind of situation. You can get pretty good mixing with some investment of power, but then if you keep pumping in more energy, the resultant effectiveness, the delta may not be very significant. So, just like for example, we talked about this in the shape assessment scenario, you may have to make certain decisions about what is the optimum point, how long do I want to mix, how much power do I want to invest into it, where do I stop the process, that kind of thing. And so, there are certain judgments and decisions that you have to make in mixing of particulate solids that you typically do not arise when you are mixing liquids. The other question is how, for solid particulates, how do you define mixing effectiveness or mixing efficiency? It is not as simple as mixing of liquids, because again if you are trying to blend two solids, they are not going to dissolve into each other, right. In any graph sample that you take, you are still going to see two or more distinct phases representing the different particulates that you are trying to blend. And even in the case of a paste material, you will see that the composition is not entirely homogeneous. There will be local heterogeneities that you have to deal with. So, the definition of mixing effectiveness is actually based on statistics in the case of solid powders. The statistical analysis says that in a well mixed product, the distribution of concentrations must be completely random and must be very uniform. How do you assess that situation? I mean, how do you assess whether a sample that you have has uniform properties based on statistics? One convenient way to do that is by looking at standard deviation. As you know, standard deviation is a measure of dispersity within a sample. So, for example, if you have a paste and you want to know how well mixed it is, one way to do that is to take some tracer, introduce it into the paste at time 0 and then monitor its concentration distribution over time. So, let us say that the concentration or its fraction is some mu as you introduce it into the paste, okay, at time 0. Now, what you do as a function of time, you take samples. So, suppose that you take a sample or n samples, okay. Each one it has a reading, let us call that xi. So, this is the fraction of the tracer in each sample, and there are I samples that you take, total of n samples. So, each sample you measure the concentration and you get a value xi. You can also take an average of all of these readings x bar. Now, clearly as n tends to infinity, this x bar will tend to the original concentration that you introduced, but as this n becomes smaller and smaller, the deviation between x bar and mu can become larger and larger. Mu is called the population mean and the x bar is called the sample mean in statistical analysis. How about the value of xi versus x bar and xi versus mu? Xi are the individual readings and x bar is the average reading. So, clearly there is going to be a difference between xi and the mean values, the mean of the sample and the mean of the population. What you want to know is what is the total deviation of the values xi from the mean values, because that gives you a measure of how non-uniform the distribution of the two or more species are in your sample. And there is a parameter called variability S squared, which is equal to summation I equal to 1 to n xi minus x bar the whole squared divided by n minus 1, right. You are familiar with the concept of variability and standard deviation. So, you take the summation of the total deviation of the individual data points xi from the mean value divided by n minus 1, and that gives you the variability. If you take the square root of that, that is called standard deviation S. So, that is square root of this same value. You can look at this value standard deviation as a measure of mixing effectiveness. The higher the standard deviation, the less well mixed the sample is or the material is, right, because a higher standard deviation implies that the individual measurements of xi differ significantly from the mean value. And so, if you plot this as I versus xi, this may have a distribution that looks like this. The mean value x bar may be here, but the individual values may be normally distributed, but with a very wide tail. So, in a situation like this, your S value can be quite large, whereas if for the same mean your distribution is like this would mean that S is small. So, clearly this is a well mixed case and this is a poorly mixed case. Okay. Now, the value of S at time equal to 0 will be maximum, and then it will slowly decrease as mixing happens. Hopefully, if your mixing process is effective, then the value of S, if you plot that as a function of t, should decrease and reach some kind of a asymptotic value. This is in a mixer which is working well, functioning effectively. But as I said, there could be cases where you kind of go like this and then the standard deviation starts to increase again. So, you need to kind of keep your eye on the behavior of the material that you are trying to blend and really understand its mixing characteristics. Another way to look at mixing effectiveness is through something called the mixing index. The mixing index, let us call that I subscript P, where P stands for paste, is defined as the value of the standard deviation at time 0 to the value of your standard deviation at time t. So, it gives you a measure of how mixing changes over time. So, if you take your S value and your, let us call that sigma 0, where sigma 0 is your standard deviation at time 0. Now, what is standard deviation at time 0? At time 0, what is happening? You have two constituents that are not mixed at all, right. So, if you take a sample, you would either say that it is the material that you are looking for or it is not. So, for example, if you are trying to measure the concentration of component A, if you sample at a location where there is component A, you will say that its fraction is 1, whereas if you sample at a location where you only have component B, you will say it is 0. Or in the case of a tracer, you will say that at point A, either xi is equal to 1, it is all tracer, or xi equal to 0. So, it is kind of a bimodal situation, it is a 0 or 1 situation. In a case like that, sigma 0 is defined as square root of mu times 1 minus mu, where again mu is the initial concentration of the tracer in your paste. So, if I look at this ratio of sigma 0 to S, at time equal to 0, it is 1. As time increases, S is going to keep decreasing, and so this ratio will keep increasing, right. So, I mean you can substitute for S from that expression, and so IP or the mixing index is going to be summation I equal to 1 to n xi minus x bar the whole squared divided by n minus 1 square root, and you have the mu times 1 minus mu also in the numerator, right. So, this is the definition of mixing index for a paste. If you plot T versus IP, what is this going to look like? So, let us say that this is 1, 10, 100 and so on. At time 0, it is going to be equal to 1, because the definition of this is the standard deviation at time 0 divided by standard deviation at time t. With the passage of time, this is going to keep increasing, right, because S will keep decreasing. The measured standard deviation keeps decreasing as a function of time. So, you will get a curve that looks like this. What is the theoretical maximum for IP? Infinity, because if you have a really good effective mixing process, eventually the standard deviation should go to 0. In other words, it should be a perfectly well mixed mixture where every value that you take is equal to the mean value, but it never happens in reality for two reasons. One is, mixing is never 100% effective. Two, your measurement technique itself has errors. So even if xi and x bar are identical, there will be a sufficient gauge error in your measurement method that will make them seem different, right. So you will never really reach infinity, but what does happen is you reach a value that is maximum values of this IP, the mixing index, tend to about 150 to 200 range. Now if you do this for different materials, you will get very different behaviors. So for example, if you are doing this for a light paste, maybe just sand with a little bit of moisture in it, you may get a behavior like this. Whereas if you do this for a slurry where you have maybe some particles that are mixed in with some surfactant or solid, you may get a behavior like this. And if you do this for wet cement, you may get a very different, the qualitative behavior is still the same. You start from 1 and you reach a maximum asymptotic value and then you stop there, but the asymptotes, as you can see, are very different in the different cases. The other parameter that is of interest here is dip by dt, which is called the rate of mixing. So the dip by dt is basically the slope of these curves as a function of time. The rate of mixing depends on two things. One is the material itself, how blendable or how mixable the material is. As you can see, the different materials will have completely different properties. The second is it depends on the mixing equipment. For example, this may be the behavior in a simple kneading type of device, whereas if you did the same kind of thing in a centrifugal tumbler, you may get very different curves. You may get a very different slope of these curves. The qualitative behavior will still remain the same. You will still see initially a steep increase in the mixing effectiveness or mixing index, but eventually you will see a asymptotic behavior. So that qualitative nature will not change, but the actual magnitudes will differ depending again on the equipment that you use for the mixing and the properties of the material that you are mixing. Okay. So the behavior that we have been talking about so far is for what we would call paste. A paste is something that is a solid mixture, but with some behavior that is analogous to that of liquids. So it is like a highly viscous liquid, you can think about it that way. For example, wet cement. But you can also think about pure solid particulate mixtures. For example, if you just take sand and salt and mix them together, right, that has a very different mixing behavior compared to one which has a wet slurry type of characteristic. So what would be the main difference? For one thing, in the case of a solid mixture, the reference value that we have used here is the standard deviation at time 0. In the case of a mixture of two solid materials, the reference value is what is known as the equilibrium or fully mixed standard deviation, which is not equal to 0, because the difference is that when you are mixing, say, sand and salt, again when you take a sample from this, depending on the size of the sample, each sample that you take may have a different ratio of sand to salt even in a well mixed powder. It depends on the size again of the sample. If you take a sample that is very large compared to the individual dimensions of the sand and the salt, you are likely to get a value that is much closer to the mean value. But the smaller your samples are and the fewer the number of particles in each sample is, the more likely it is to deviate from the population mean. So, in the case of mixing of pure solids, the reference standard deviation is this sigma e, which stands for the equilibrium standard deviation, and it is not equal to 0 even under well mixed conditions, and in fact it has a value that is equal to square root of mu times 1 minus mu, same as sigma 0 earlier, but with one difference, that it is divided by your sample size n, which is the number of particles in each sample that you take. When n is equal to 1, obviously sigma e is equal to sigma 0. In other words, if each sample that you take has only one particle in it, then it goes back to the earlier case, that particle may either be a tracer particle or not, right. So, in the case of n equals 1, the two converge, and sigma e in the case of solids mixing becomes the same as sigma 0 in the case of paste mixing. So, in the case of solids mixing, the way you would define the mixing index is as sigma e by s, or again you can substitute in that expression and summation I equal to 1 to n xi minus x bar squared times mu times 1 minus mu, but here you have n times n minus 1. Again, n is the number of samples and n is number of particles per sample. So, capital N is the number of samples and n is number of particles per sample. Any questions?
So that sigma comes down, denominator.
All right, in both of these, let us see, at time equal to 0, IP equal to 1, as time increases, S will become smaller and smaller, right. So, IP should become larger and larger, right.
That summation term comes denominator.
Oh, sorry, yeah, this should be in the numerator. Okay, guys can make that correction. Okay, so the definition of IS or the mixing index for solids is different from the mixing index of a paste, again based on the fact that in one case the reference standard deviation is your initial condition, and in the case of the solids the reference condition is your equilibrium condition. But for a solids, what is the mixing index at time equal to 0? It is actually the ratio between sigma e and sigma 0, or it is equal to 1 by square root of n. The mixing index at time equal to 0 for a solid mixture is 1 by square root of n. Again, n is the number of particles that you have per sample that you take, and if it is equal to 1, then the initial value of your mixing index for solids is also equal to 1. In the case of mixing of solids, if you plot the same thing, if you plot T versus IS, let us say that this is a tumbling mixer and you are mixing sand and salt. Okay. If you plot T versus IS Do you think it will have the same characteristics as the as for a paste, or do you think it will be different? For one thing, you never go to values as high as 100 or so. In fact, in this particular case, the maximum is about 1 in the case of by the way that the definition, because you are using the equilibrium value as your reference value, the maximum value that IS can have is only 1, right. And we know that it is never going to be equal to 0, because there is always going to be some finite amount of mixing even at time 0. So, if you look at how this behaves, the kind of behavior that you see is again initially there is a rapid rise, but then sort of a fluctuating behavior followed by a tendency for the mixing to get worse over time. So, in fact, the maximum you get to is about 0.7 or so, and then it starts fluctuating in this region between 0.4 to 0.5, and eventually it starts to take a dive. And again, the reason that this happens is for two reasons. One is just segregation and the other is agglomeration. The behavior of solid mixtures in a blender is never a monotonic behavior. Just because you do it longer does not mean you are going to get better mixing. You may actually start to have adverse effects due to, it is just like grinding, right. If you are trying to do size reduction by ball milling, you will see a size reduction up to a certain time, but then the material will actually start to re-agglomerate, and therefore you will start to see a reduction in the size reduction efficiency with the passage of time. Similarly, in mixing of particulate solids also, you will start to see a degradation in the mixing index with the passage of time. So, you have to design the process so that you capture, I mean the time for mixing has to be set in such a way that you are in a region where you are reasonably stable. The problem with doing it somewhere in this time ranges, even a small change in time can make a huge difference to the mixing effectiveness. So, the process becomes highly unpredictable, whereas if you keep your time in this range, you can be reasonably sure at least what window your mixing index is going to be. So, the ideal or optimal time frame would be somewhere in this range. Now, if you look at the rate of mixing in this case, how would you define it? Just like we did with the paste, you can define a dIs by dt, but in this case you can actually give it a mathematical expression, because you know that the equilibrium value is 1, and you know the driving force for any process is the deviation from equilibrium. Any process tries to attain equilibrium. So, the departure from the equilibrium value can be looked at as the driving force for mixing to happen. So, in this particular case, your ultimate value for IS is 1. So, you can kind of look at that as your limit, and the difference between that equilibrium value and your current value provides a driving force for mixing to happen. So, you can simply write dIs by dt as equal to k times 1 minus IS. So, it is the deviation of your mixing index from its ultimate value of unity that drives your mixing process. So, the process tries to get to a mixing index of 1. So, if you solve this, you will get an expression like IS equals some 1 over k times ln of 1 minus IS 0 over 1 minus IS. But we have seen before that IS 0 has a value of 1 by square root of n. So, the value of IS as a function of time is going to be equal to the rate of change of There has to be a time somewhere, right? Anyway, this is the expression for how the mixing index changes as a function of time, and when you integrate it you will get the value. Just make sure that you substitute 1 over square root of n for the time 0 value of the mixing index. When you solve this you should get an expression that looks like the behavior that you would see when you plot T as versus the mixing effectiveness for a solid. So what we have looked at today is the behavior of mixing of pastes and solids. Now as I was saying before, the nature of these curves can change, particularly in a quantitative way, depending on the mixing equipment that you use. And so it is important to understand the variety of mixing equipment that's available in industry. So I will circulate a PowerPoint that talks about the various types of mixers in industry, and you should take a look at it just to become aware of what is happening in terms of industrial applications in the area of mixing. And similarly I also mentioned that transport or conveyance of solids is another important mechanical operation for which there are many different varieties of equipment that are used in industry. So I will circulate and upload a PowerPoint on that also, so take a look at it. And then so in the next lecture we will start talking about another important mechanical operation that's used widely, and that is fluidization and the various processes in which it's used and some of the principles behind it. Any questions? Yeah.
How do we use a tracer to determine concentration in a particular sample?
See, there are two ways in which you can test for mixing effectiveness, right? If you have, let's say, 10 constituents in a mixture, one way to test for uniformity is to take samples at different locations, measure the concentrations of each of the constituents, and the concentrations have to be uniform. The other way to do it is simply using a tracer as an indicator of mixing effectiveness, because now you can just track the concentration of that one tracer. So you take the concentration of that tracer at different points, and the tracer concentration also gives you an indication of how uniformly it's distributed. But the tracer approach works better in the case of pastes. In the case of solid particulates, we have to really look at the concentration of the individual, or the number fraction of the individual particles.
Is there a difference between the concentration of a particular species in a mixture in a paste and the concentration of the tracer?
Certainly the tracer can behave very differently. That's one of the downfalls of using a tracer to assess anything, whether it's a chemical reaction or whether it's mixing effectiveness. The tracer itself is a chemical species, right? So it will have characteristics that are very different from the reactants and the products that you're tracing. So it's certainly possible that the mixing effectiveness that you assess by using a tracer may not be representative of how the individual constituents may be mixed. It's more an indicator of how the mixing equipment is behaving rather than how the materials will behave in that equipment. Okay, see you next class.